Okay, if we could have quiet, please. We're now ready to start chapter 4, where we move on. Having introduced the open sets, we're now going to look at some more interesting properties of the open sets, and we're going to look at closed sets as well. And it's very important that you know the difference between a closed set and a set which is not open. And that's going to come in again and again. See the frequently asked questions document for the module for lots of big warnings about that. And it does seem to be a big problem when I'm teaching this module. It's very hard for people to get into their heads the difference between closed and not open, which are very different concepts, as we're going to see. So we're going to start this chapter with an easy lemma, which says that if you make a set bigger, then you can't make the interior smaller. So in other words, if A is a subset of B, then the interior of A is a subset of the interior of B. So let me prove that for you. So what we have to do is take a point in the interior of A and prove it's in the interior of B. So we let X be in the interior of A, and we have to prove that X is in the interior of B. Now this is rather easy because, well, I'll just draw you the picture first of all. This is an optional picture. Well, you've got your point X, and X is inside A, and A is inside B. But more than that, X is in the interior of A, so you can find a little ball round X, which is completely inside A. So that will be a little open ball centered on X, which will be inside A. Now this diagram is not a proof, but it does tell you why this thing is going to be true. Since X is in the interior of A, I can now go back to writing the formal proof again. There is some small positive real number R, so that the ball radius little r centered on X is entirely contained in A, is a subset of A. But A is a subset of B, so the same ball works for B. So we also have the same ball is contained in B, and so of course that means X is in the interior of B. And that does it. Every interior point of A is also an interior point of B, just because A is a subset of B. That's dead easy. Note, however, it's a very good example of one of our very direct proofs. We had some information, we have some definitions. I used all the information when it was available at the appropriate points, using the definitions when I needed to, And the proof actually wrote itself. And of course it was an easy proof. There really wasn't much choice about what you could do at any stage. Okay, so what are we going to do with that? Well, based on that fact, well, we'll use that to prove that the union of two open sets is open. We'll have to have a different proof for the intersection. So let's do the union first. So you're given U and V are open subsets of R to the D. We prove that U union V is open by proving it's equal to its interior. And in fact, it's enough to show by showing that it's contained in its interior, that U union V is a subset of the interior of U union V. Why is that enough? Well, the reverse inequality is automatic. The interior of any set is a subset of the set. So if we get that, equality follows. And if a set's equal to its interior, then it's open. So all we have got to do is prove that inclusion. But to prove that inclusion, it's enough to show that U is a subset of the right-hand side and that V is as well. So the set inclusion U union V contained in the interior of U union V will follow if we can prove the following. This is not the only proof, by the way, and if you look at the notes from last year, you'll find a completely different proof. It's enough to prove that U is contained in the interior of U union V and that V is contained in the interior of U union V. If you have both of those, if you have two sets both being a subset of the same set, then their union is also a subset of that set. So that will do it, if we could do it. But this is quite easy because that U is definitely a subset of U union V. So the interior of U is contained in the interior of U union V by the previous lemma. If you make a set bigger, you can't make the interior smaller. But U is open, so U equals interior of U. Since U is open, U equals interior of U, and so U is contained in the interior of U union V. And now the proof for V is exactly the same. The same proof shows V is contained in the interior of union V. Thus, the union is and it follows that U union V is open. I'll put in the extra step here. U union V is actually equal to the interior of U union V. So U union V is open. Unfortunately, we can't really use that trick for the intersection. The intersection needs its own proof. So to prove that U intersection V is open, again, given that U and V are open, remember, we've got to use the fact that U and V are open somewhere in our proof. Let's say, suppose X is a point of U intersection V, then we have to prove it's an interior point. So we show every X in U intersection V, which might be empty, by the way. If you want, you can treat the case where the intersection is empty as a special case, but the proof I'm about to give is actually valid in that case as well. Because I'm going to say, suppose X is in a minute. So we're going to show that every X in U intersection V is in the interior of U intersection V. Now, it would be very slightly dangerous to say, let X be the intersection, because there might not be any. But I am allowed to say, suppose that X is in U intersection V. Then X is in U and X is in V. Now, since U is open, that means, oh, I should have some underlinings there. Since U is open, X must be in the interior of U. There'll be some positive real number, we'll call it R1, so that the ball centered on X radius little r1 will be contained in the set U. So since U is open, there exists a number R1 greater than 0, a real number, a positive real number R1, probably quite small, with BR1 of X contained in U. And similarly, since V is open, and X is in V from above, there exists an R2 greater than 0 with BR2 of X contained in V. And now we get another one of these optional diagrams, which you don't have to give in the proof, but which do show you what's going on. So here, say, is U, and here is V. And here's your point X, which is in the intersection of the two of them. When in this picture, it looks like X is nearer the edge of V than it is to the edge of U. So it could be that in this picture, which is not going to actually prove the result, but it's going to show you what's going on. In this picture, it looks like you could put a little ball round X inside V like this. So that's BR2 of X. And there's room for a slightly bigger one round X that's inside U. But as long as you take the smaller value from R1 and R2, you're guaranteed to stay inside both. So we'll set little r to be the minimum of those two values, R1 and R2. We don't know which it is. And note that since R1 and R2 are both positive, so is this. Then if you take that small radius, the ball is contained in U and that ball is contained in V. So in fact, that ball is contained in the intersection. It's actually equal to the intersection of those two balls shown there. So in fact, BR of X is then contained in the intersection. And this shows that X is in the interior of U intersection V. But that was true whatever X in U intersection V you took. So U intersection V is open. And that's a slightly trickier proof. That proof had an idea in the middle of it. The idea was based on the diagram. You had two values. Most of it wrote itself. You had to remember that the R1 and the R2 might have been different in the first place. You've got an R1 that kept you inside U, and an R2 that kept you inside V, and then you had to have an idea as to how could you stay inside both U and V at the same time. Answer, take the smaller of the two values, and that will guarantee that you stay inside both. Any questions about that proof? As I say, if you do come up with any questions, you're welcome to drop it on office hours, send me an email, whatever. So now, if you take 3 open sets, and you intersect 2 of them together, that'll be open, and then intersect it with the third open set, then it'll still be open. So if you intersect finally many open sets, you'll still get an open set. And remember, if you do end up empty, you could treat that as a special case, but we know the empty set is open, so that's all right. But the proof actually does work that I've given there, it's just you have to think about it a bit. And unions as well. Finite unions are okay. So you can intersect finitely many open sets together and stay open. You can take the union of finitely many open sets and stay open. But something interesting happens if you take infinitely many. It turns out that you can take a union of as many open sets as you like, and you're guaranteed to still be open. But that isn't true for intersection. If you take an intersection of infinitely many open sets, then in fact you might not be open anymore, as we'll see by some examples coming up later. Well, let's explain about these infinite unions and infinite intersections. So what are infinite unions? Well, we're perfectly happy with taking a union of finitely many sets, just by saying A1 union, A2 union, and so on. And here's one of the formulations of it. It means that you should be in at least one of the sets AI. To be in the union, you have to be in at least one of the relevant sets. So suppose you've got an infinite number in some list, in a sequence. So you've got a sequence of sets now. A1, A2, and A3, they're all sets. And now we can define the union of them all with 2 equivalent notations. So that means the union of all the sets AN, where n runs through the natural numbers. So that means n runs through 1, 2, 3, 4. You can also allowed to write it as the union from n equals 1 to infinity, as long as you remember there is no infinity of set. This is a bit like series notation. When you sum a series, you're summing the first, second, third, and fourth, and so on term. There isn't an infinity of term to add in. So this is just purely notational. just like the sum from n equals 1 to infinity is notational, there isn't an infinity of set here. And it just means those points x which are in at least one of the sets that you've mentioned. And we call such a union a countable union, and that's because you don't have to use the natural numbers as the indexing set. And for those of you who've met countability and uncountability, you can have unions of uncountably many sets. And in fact, it turns out that a union, even an uncountable union of open sets is still open, but we won't do uncountable unions in this module. If you're interested in different kinds of infinity, you might want to look at my movie about the different kinds of infinity called Beyond Infinity, and that's available on the University U Now site. Actually, it's also available on the Nottingham YouTube site as well. That's called Beyond Infinity. So our next trick is to well, let's have a look. Our next trick is to prove that even if you take a union of infinitely many open sets, you're still open. I use a slightly different proof structure for this. You could base this on the previous idea, but I'm going to use the other proof method this time. So you've got this sequence of open sets. So you've got lots of open sets, U1, U2, U3, one for every natural number. And now you take the union of them all. The union of them all consists of those points which are in at least one of the open sets mentioned. And the claim is that it's still open. So let's prove it. So we have to prove, again, that every x in the union is in the interior of the union. So again, you can either say let, but if you say let, it's very slightly a bit dangerous, because actually all of the UNs could be empty and then the union would be empty, which would be a special case, which would be easy to deal with. But if you want to be really safe, you could say suppose that x is in that set. And from that, you have to deduce that it's in the interior. Well, there isn't a lot of option at this point. We have to use the definition of union. If x is in this union, it means that it's in at least one of the sets. To be in at least one of the sets means that there exists some number n naught so that x is in that particular one. That's what it means to be in the union. You have to be in at least one of the sets, so there must be some number n naught so that you're in that set. But then, un naught is open, so x is in the interior of un naught. Is open, so every point of un naught is an interior point of un naught. And finally, un naught is just one of the sets, and therefore is contained in the whole union. So, since un naught is contained in the union from n equals 1 to infinity, any one of the sets is contained in the union of the lot, then we know that the interiors have the same relationship. So the interior of un naught is a subset of the interior of the union. Union, not U. with unions and U's flying around, I sometimes wish I'd chosen some different letters. But hopefully you can tell the difference between my unions and my U's. So what have we got? Let's have a look at this. X is in the interior of UN naught. The interior of UN naught is a subset of the interior of the whole lot. So X is in the interior of the whole lot. Now, strangely enough, that's exactly what I said we had to prove. We've shown that whenever X is in the union, it's in the interior of the union. So since this is true for all X, that's for all X in the union from n equals 1 to infinity of UN, that union is open. Okay, doesn't matter how many you've got, take their union, it's still open. And actually, even if you've got uncountably many, the same proof works. Now, if you want to do intersections, you've got a similar idea. Suppose you've got infinitely many sets, and you want to intersect them all. Well, you're looking at those X which are in all of the sets simultaneously. Now, people do find this a hard concept to work with, and in fact, some of the examples we're going to look at have given people a lot of trouble in the past. It can be actually quite tricky to work out which points are in an infinite intersection. And this is one of the reasons why it's a bit odd that if you intersect infinitely many open sets, you sometimes get a set that isn't open anymore. But let's have a look at an example. Actually, I think we've got time that you could have a go at this. Consider the open intervals UN equals minus 1 over n up to 1 over n. So each of these is an open subset of R. What is the intersection of all of these? And I'll just give you a hint. X is in the intersection of these. I'll just remind you the definition. If and only if the following statement holds about X. For all natural numbers n, we have minus 1 over n less than equal to x less than equal to 1 over n. Less than x less than 1 over n. So let me give you a little bit of time to think about which real numbers might satisfy that condition, if any. And I'll pause the recording and let you have a think about this. Right, so you've had a little bit of time to think about that. Now, I have seen some mistakes in the past in the exam when this example has been known to turn up, and people have said, well, let n tend to infinity, and then you get the open interval 0, 0. But the open interval from 0 up to 0 has no points in it. And that's incorrect. There is at least one point in this set. Who can tell me a point that is definitely in this set? 0 is in, okay? But there aren't any others. 0 is the only point that's in this intersection. So let's have a look at that condition, call it star. It's easy to see that 0 does satisfy star. Since minus 1 over n is smaller than 0, strictly, is smaller than 1 over n for all natural numbers. So that's okay. So what does that tell you? That so far, what you've got is that 0 is in the intersection. We claim that there aren't any other points that satisfy condition star. And then you've identified what your set is. So we claim there are no other solutions to star. And there's lots of different ways to do this. I'll do a proof by contradiction for once. You don't have to do this by contradiction, but I will do it by contradiction for once. Suppose for contradiction that x is a real number with x not equal to 0 and that x satisfies star. Well, if x is not 0, then mod x is greater than 0. So, since 1 over n tends to 0 and then tends to infinity, there exists a big positive natural number n with 1 over capital N smaller than mod x. But then x is not between minus 1 over n and n. And this contradicts star because it's supposed to be between them for every natural number. So there are no such x, and that means 0 is the only solution. In other words, the intersection from n equals 1 to infinity of those open intervals is the single point set with just 0 in it. And it's a standard fact. We've already got this. It's a standard fact. A single point set is not open. We did that before. Well, we mentioned it before. Or you can check for yourself. Obviously, it's got one point, and that point is a non-interior point. It's definitely not open. So here you've got it, an intersection of infinitely many open sets giving you a set which isn't open anymore. But if you stopped at any finite stage, you've got these shrinking intervals. If you stop at a finite stage, you get the smallest interval so far, a nice open interval. But by the time you've done infinitely many intersections, something changes. It's a sort of change in the limit. And the set you get to at the end is not open anymore. Any questions about that example? Well, I think that's a good place to stop. We'll be doing closed sets next time.